doing apportionment. Here's an example of what's known as an apportionment problem. Mom has a total of 50 pieces of candy, which she is planning to divide among her 5 children. But rather than just dividing it equally and giving 10 pieces per child, she is going to use this as an opportunity to teach her children about the relationship between work and reward. So she announces to her kids that the candy is going to be divided among them at the end of the week in proportion to the amount of time each of them has spent on chores that week, right? So if you worked twice as long as your brother, you're going to get twice as much candy, etc. Okay. So here are the numbers at the end of the week for each of the 5 kids, how many minutes they spent on chores. Total of 900 minutes were done among the 5 of them. Take some time in your groups and find a solution. How much candy you're going to give to each kid? So I saw, as I walked around, like 3 different approaches to how to figure out how much candy to give to each child. All completely valid and actually all equivalent, just sort of coming at the problem in a slightly different way. All right, so method 1 was percentages. So you figure out what percentage of the work each child did, and they should get that percentage of the candy, right? So for example, let's just do Alan, right? So we figure out what percentage of the work Alan did. He did 150 of the 900 minutes. So 150 over 900 comes out to what as a percent? 16.6? 16, is it 0.7? Doesn't matter. 16.7% of the work, right? So that means we should give Alan 16.7% of the candy. So 16.7% of the 50 pieces. How do you calculate this? Yep, so you do 0.167 times 50, and that comes out to how many pieces? 8 point what? 3? 8.3 pieces of candy. Okay, so you could go through and do this calculation for each child. Okay, method 2 that I saw had to do with the number 18, right? So if you take 900 minutes and divide it by 50 pieces of candy, right? This reduces to 18, right? This reduces to 18 over 1. And so this says 18 minutes per 1 candy. So that tells us that every 18 minutes worked earns each child a piece of candy. So let's see, who's the B? Betty, right? So Betty, we say she worked 78 minutes. Divide that by 18 minutes per piece of candy. So we figure out how many sets of 18 she worked, and that will tell us how many pieces of candy she gets. And what does that come out to? 4.3. So this one's the quickest, because once you do the 18 calculation, you just have to divide each child's work by 18. So 173 divided by 18. What? 9.6. Okay. And that's Connie. I don't remember how to spell Connie. And Doug. $204 divided by 18 comes out to 11.3 pieces, right? I'm actually going to do Ellie a different way just because I want to show the third method. Okay. All right, third method that I saw as people walked around was to set up a proportion. Okay, so we would say for Ellie did 295 of the 900 minutes, right? So we'd say 295 of the 900, part to whole, right? The part of the work that Ellie did compared to the whole amount of work should equal the part of the candy compared to the whole amount of candy that Ellie gets. So part we don't know, whole amount of candy is 50. Part to whole equals part to whole. We set up a proportion, and you remember you solve this by cross multiplying. So we would say 900x, 900 times x equals 295 times 50. 295 times 50 is 14,750. And then you solve that equation by dividing both sides by 900. And we get x equals 16.4-ish. 16.4 pieces of candy for Ellie. Okay, so we so we know exactly how many pieces of candy each child has earned, but we can't. I didn't tell you this, but you can't give out a piece of candy, right? Imagine they're hard candies, right? You can't cut them into pieces, right? So what are we going to do? How do we decide how many pieces to give each of these kids? Round, like standard rounding. So we would have Alan gets 8, right? Betty gets 4, and Connie gets 10, and Doug gets 11. And Ellie gets 16. All right, what does that add up to? 49. Okay, that only adds up to 49 pieces of candy. So who do you give the extra one to?
Ellie.
Ellie? Why Ellie? Because she did the most work. Who else could we give it to? Betty for sympathy. Yeah. She got the least amount of candy. Poor Betty. We'll give her the extra. Who else could we give it to? Mom could keep it. Yeah. Mom could keep it, save it for the next game, or eat it herself. Whatever. So this is the decision. This is what makes an apportionment problem hard, right? Figuring out the exact amount that each child earned is a relatively straightforward math problem. You were all able to solve it without me telling you how to do it at all. It's what do you do with the little bits? Who do you give them to in a fair way? So the common place where we see an apportionment problem isn't just in a household, you know, dividing candy among children, but sometimes we're in a situation where what we're dividing are really valuable things, right? Like seats in a Congress, right? And people have a high stake in wanting to get the extra, right? Each one is really valuable. So giving out those little pieces becomes important. Who gets the extra becomes really important. All right, so here's an example. Parador is a fictional country consisting of 6 states, creatively named A, B, C, D, and E, and F. And there are 250 seats in the Congress, which, according to the laws of Parador, are to be apportioned among the 6 states in proportion to their populations, right? So if one state has a population double another state, it should have twice as many seats in Congress. So what is the correct apportionment given these population figures? So we're not going to use all 3 methods. I'm just going to do method 3, where we figure out how many people equals 1 seat in Congress. So I have how many people total? 12,500,000. And how many seats? 250. So if I take 12,500,000 people, oops, another zero, people, divided by 250 seats. That comes out to 50,000 people per one seat. This is the third method, yeah. We call this number a standard divisor, because now what you're going to use this number for is divide every population by 50,000. Because every set of 50,000 people gets you a seat in Congress, so you have to figure out how many sets of 50,000 are in each state. Okay, so we call this number the standard divisor because we're going to use it to divide, right, each population. So we take the calculator, divide each population by 50,000. $32.92, and then $138.72. So one little thing you can do when you have a shortcut is when you're dividing, you can just cancel all the zeros, right? So if I have 154,000 divided by 50,000, I can, if I have 3 zeros on top and 3 zeros on the bottom, you can cancel them and you can just do 154 divided by 50. Just saves you a couple of button presses. 3.08. And then I can do 2091 divided by 50, 41.82. And 685 divided by 50, 13.7. 988 divided by 50, 19.76. Now, if I did all my calculations correctly, what should these add up to if I add up the total number of seats I have here? 250, right? Because this is the exact share that each state deserves. If I could give out a piece of a seat, I would give 32.92 seats to state A. It's the exact number that they should get. So when I add these all up in my calculator, I should get 250, and that's a good way to check if you did everything right. Okay. So we can calculate the exact number of seats that each state should receive, but the problem is that you can't give out a partial seat. So let's go back and look at our numbers here. How could I decide what to do with my extra pieces of? Yes.
How much each state has total
So look at the leftovers. Yeah. Okay, so like 32.92. That number, that state is the closest to getting a whole nother seat, right? So maybe we'll give them the first extra seat, right? Right, so we can look at the remainders. Right? And I will round, you know, sort of standard round until I run out of seats, right? What else could I do? If I add up the remainders, Emma, yeah.
that's kind of where I'm before it's talked about the ratio method.
Mm-hmm. By the total?
Yes.
Ah, so you would take like 0.92 and divide by 250 and see what percentage that is? Sure. Yeah. If you're going to divide them all by 250, you can just compare the remainders themselves, right? Because if they're all getting divided by the same number, then they'll come out in the same order in terms of size. So this, if you're all going to divide all of them by the total, you actually don't need to do it because the relative sizes will stay the same. But I think that what your brain is like, I think that you have a different idea. And this is a method that we're not actually going to learn in class, but it is a method that was proposed and used. So if you look at the 0.92 and compare it to the whole part, that will tell you what? What does that tell you? What percentage of the population is sort of unrepresented? Yeah. And then you give it to the largest percent of this, whatever this number is largest, because you want to have the largest, whichever state has the largest unrepresented population, or largest percent unrepresented. So yeah, this is a really great method. That's nice. This is called Lowndes method, and we're not actually going to learn it, but it's a good one. So it all has to do with the remainders, right? So before I go ahead and tell you sort of the answer, we're gonna just talk about a little bit of vocabulary. Because this apportionment problem occurs so frequently in divvying up congressional seats to states, we call the term that for parties that have a stake in the apportionment, they're going to be called the states, right? So in the kids example, the kids were the states. And the seats is the term that describes the identical, indivisible objects that are being divided. So in our very first example, that was the candy. The candy was the seats. And an apportionment method is a systematic method that divides the seats among the states. The standard divisor, already told you about that, is the ratio of the total population to the number of seats, and it measures how many people per seat. Standard quotas, this is not a word that I used yet. It is the exact number of seats each state should get if fractional seats were allowed. So these, what I have up here, those are the standard quotas. And then the upper and lower quota is what you get when you take the standard quota and round it down. That's your lower quota. If you just chop the decimals off of each of these, you get lower quotas. And if you bump them up to the next number, you get upper quotas. All right, so how to apportion, oops, little typo. How to apportion electoral votes and seats in the House of Representatives has been a recurring debate in U.S. history. So this is two places that we use apportionment. We have to decide how many members of the House of Representatives each state gets, and we have to decide how many electoral votes each state gets. And we do it the same way. It depends on population size. So it's actually the same problem, right? However many representatives you have in the House, that's how many electoral votes that state gets. So this is just an example to show you about the Electoral College. Oh, I meant to pick a map that had numbers on it. Oh well. Oh, I think it was maybe too close to call. Yeah, that's my guess. Gray would be too close to call. Yeah, it could have been decided before. Maybe this picture was made before it was Florida was decided. Yeah. So we're going to study several historical ways that the United States has solved this apportionment problem. And we're also going to look at the current method that's used for apportionment in the United States. So you're going to be hearing lots of familiar names if you've studied any U.S. history at all. The first one is Hamilton's method, named after Alexander Hamilton. Yep. So Hamilton's method, and this is kind of the amazing thing, is that these guys weren't mathematicians, right? They're just pretty smart guys who thought of how to do this on their own. So his method is calculate each state's standard quota. Give each state its lower quota, that is just chop off the decimals and give them the whole part that they deserve, right? Then you give the surplus seats one at a time to the states with the largest residues. That's the largest decimal piece until there are no more surplus seats. So we're going to use Hamilton's method to finish the apportionment for Congress of Parador. So this is the one we just set up. We've got the standard quotas. Lower quotas, you just chop off the decimal. So we've got 32, 138, 3, 41, 13, and 19. And when you add those up, we're going to have fewer than 250 because these numbers are all smaller than the standard quotas. So 32 plus 138 plus 3 plus 41 plus 13 plus 19, 246 seats. So that means I have 4 seats left over. And Hamilton said I should give these 4 seats to the 4 states with the largest decimal piece. So now look at the decimal part that you chopped off before. We've got a 0.92, we've got a 0.72, we've got a 0.08, we've got a 0.82, a 0.7, and a 0.76. If you add up these decimal pieces, what should you get? 4, because there are 4 seats missing. Yep. Okay, so which state has the largest decimal piece? A. So we are definitely going to give A one of my 4 surplus seats. Who's got the next largest? D. They're going to get the second surplus seat. Who's got the next largest? F. They get the third. And the next? B. They get the 4th surplus seat. So everyone gets at least their lower quota, right? Everyone gets at least the whole part with the decimal chopped off. And then some states are going to get an additional seat, the ones with the largest surplus. So state A gets their lower quota, 32, plus another seat, so they get 33. And B gets their 138 plus an extra seat, so they get 139. State C got 3 seats, and they didn't get any of the surplus because their decimal piece was not in the largest 4. So they just get 3. Right? No extras for C. And then for D, they get their 41, their lower quota, plus an extra, so they get 42. E, 13 is their lower quota. They didn't get one of the extras, so they just get 13. And then F gets 19 plus an extra, which is 20. And now when you add them up, you should get 250. And there's our apportionment, our final apportionment. Okay, you try one. Okay, so it looks like everybody feels pretty comfortable with this and has the correct answer, which was down here. If you didn't see it, you can compare your answer to this. I think it's right. All right, we'll go through it. If a couple people got it wrong, we'll. Oh, because there were only 3 surplus seats. Yeah. So yeah, you have to. If you were following my example, you might have given out 4 seats because we had 4 seats in this example, right? But you figure out how many surplus there are by adding across and seeing what the total is and subtracting from how many you have. Okay, so what do you like about Hamilton's method? Easy, okay. What else? It's not fair? you like that it's not fair, okay. What's not fair about it?
It rewards like the people with more votes get more votes. That seems like according to the population.
Yeah, and since we talked about Lowndes' method earlier, you percent unrepresented might be a better way. Yeah, go ahead. if we were going to use.
Choices, obviously, all their choices are going to go over.
Oh, okay. So you're confusing this with a voting method, where what we're doing now is we are apportioning votes to states, right? So we would have the 50 U.S. states and their populations. So am I not understanding your question? Okay. Okay. All right. Is there anything else you like about it? Easy, fast. Yeah. Yep. So and it kind I mean it makes sense, right? That whoever is closest to getting a whole nother seat gets a whole nother seat, right? Yeah. What are the cons?
Well, like what I was saying is if there's the number of seats is like 32.2,
Uh-huh.
and then another state has 31.9.
Yeah.
31.9 is gonna get the extra seat, and they're gonna be tied.
And they're going to have equal power, even though the other one actually had more population. Yeah. Yeah, so there are a lot of cons, and that's why we're saving the cons for a whole separate class. But easy, fast, and seemingly fair. I'll write seemingly fair. On the surface, it seems fair, right? Seems like a good method, but we're going to spend a whole nother class talking about the drawbacks to Hamilton's method. All right, so the remainder of this class, I want to spend introducing you to Project 2, because it is harder than Project 1. Shh, please, quiet. Okay, so your project is to apportion the 435 seats in the House of Representatives to the 50 states. So we're going to learn 5 methods of apportionment, and I want you to apportion it using each of those methods using formulas in Excel. So if you were to do it by hand, it would be a nightmare. You don't want to do it by hand. And there are other things that we've already covered in this class that would be a nightmare to do by hand. And I just gave you small problems, right? So if there's one skill you leave this class with, I hope it's being able to use Excel. Okay, so I have this project for you. And if you have never used Excel, like you're going to have to spend some time exploring in Excel and possibly watching some of the videos I've posted and maybe coming to my office hours if it's not clicking. So here is the actual file that is posted in Moodle. Okay, this is going to be posted in Moodle. It's an Excel file. You're just going to open it up, save it somewhere on your computer that you can find it, like probably your desktop, right? And you're going to name it your name, like Caitlin Worth, Mat 117 Excel project. Okay. Then you're going to use formulas in Excel to apportion the 435 seats in the U.S. House of Representatives among the 50 states using each of the 5 methods we learned in class. So today we learned one of those methods, Hamilton's method. There's a sheet in this workbook file to help you set up each of the methods. So the sheets are down at the bottom. There's a little tab for each of the methods. So this first tab is directions, right? And the next tab is Hamilton. And I've set it all up for you, right? So I've got the whole method set up, but you have to write the formulas to get the numbers, right? You have to figure out what the standard divisor is, and there it is. Okay. So then there's a little tab for Jefferson's method, named after Thomas Jefferson. Then we have Adams' method, Webster's method, and the Huntington Hill method, which is the method that we currently use. Okay. So this is your project. So once you have done the apportionment part, you just email me your project, because part of grading it is I'm going to look at your formulas, not just your results. I want to see that you used formulas. Okay, so you'll email me your Excel file, and then I can look through all your formulas and what you did and grade it on the computer. So these are some commands that you'll probably use while you're writing your formulas. And I said, see example handout or class videos for more info on these. So this is an example This handout I just gave you is an example. It's different. It's a different example than the 50 states example, where I'm explain how to write all the formulas. And there's screenshots and everything, so you can refer to this. I'm going to do an example right now, so you can rewatch this video. And you'll have those resources. Okay, so here's a completely random example. I'm going to do this apportionment problem using Hamilton's method. Okay, I'm going to do it in Excel so that you can see all the commands that are going to be used and you can get a flavor for how this works. And if you can't follow along right now because you've never seen Excel and you don't know what I'm doing, this is on video, right? So you can go watch it again while you have Excel up on your computer and follow what I do. All right, so this is 6 states. This might even be a problem that this is Parador, right? This is the Congress of Parador that we did in class. All right, so I have the 6 states, I have their populations. So the first thing I need is I need the total population. So to get the total population, I need to add these all together. And this is the whole point of Excel, is that Excel is a calculator, right? So you don't have to type these all into your calculator. You have Excel do this. And the way you get Excel to do a calculation, rather than just typing what you, the way you tell Excel that please do this as a calculation, don't just write what I'm typing, is you use an equal sign. Okay, so the first thing I should press is equals. And then you type what you want it to do. So you can either click each number. So you say, well, I want you to take this number and add, press the plus sign, this number, add this number, plus the number in this cell, plus the number in this cell, plus the number in this cell. So each little box in an Excel spreadsheet is called cell. It's called Excel. So then you just hit enter and it adds them all up for you. So that's one way you can get a sum, is to add each individual cell. Another thing you can do is use the command sum. So you hit the equal sign, you type the word sum. It's a known command to Excel. You open a parentheses, and then you just highlight all the numbers that you want it to add. And you can see once you type a command, it tells you what the inputs should be to use that command. And it takes a little getting used to know what format Excel uses and stuff. But so I'm going to open the parentheses and then just click and drag to highlight all the cells you want it to add up. Close the parentheses, enter, and we get the total population. 12,500,000. Okay, so then the first step in Hamilton's method was what? Once you know all the populations and the total population, what do you have to do? Standard divisor. Okay, so I'm going to make just anywhere outside of my grid, I'm going to calculate standard divisor. Maybe I'll put it down here. Standard divisor. And since I didn't use an equal sign, it just types what I write, right? There's no, make that a little bit bigger. Okay, so to get the standard divisor, I have to do what? Yes. So this is the Congress of Parador example from class. So there were 250 seats. Yeah. Yep. So I need an equation. I want to have it calculate this for me. So I hit equals. And then this number. So rather than retype it, I can just click this cell. Say take that number, divide by the number of seats, which isn't in a cell anywhere yet. So I'll just type it, 250. Standard divisor is 50,000. That a little bit bigger. Okay. Then what? What do I do for Hamilton's method? Divide each population by this number. Yeah. So I use an equal sign, and I just tell the computer, divide this. It's because I'm too big. All right, well, I'll show you another little thing you can do in Excel. Instead of clicking the cell you want, you can give its address. by giving its letter, the column it's in, and then its number, the row it's in. So I'm unable to click here, right? It's like something weird is happening apparently because my font is too big. So instead of clicking it, I'm going to say cell B2 and just give its address, column, row, letter, number. So I want it to take whatever number is in cell B2 and divide by the standard divisor, which is in cell B13. That's where that B13 comes from. Enter, 32.92. Now, I could type this formula into each of these, which is not such a big deal when I only have 6 states, right? But when you have 50 states, you don't want to have to retype the same formula over and over and over again. So Excel has this nifty little thing where if you hover the mouse over this lower right corner, you can click and drag. And people who've used Excel before know this isn't going to work. But if you haven't, I get all these like errors, right? Okay, so the problem is if you want to troubleshoot your formulas in Excel, click on your cell and you can see the formula for it up here, right? So right here, 32.92, that's cell B2, that's this one, divided by cell B13, that's the 5,000. Okay, that's perfect, that's exactly what I want. Go to the next cell, and Excel assumed that I wanted to change to cell C2, which I did. I wanted to use cell C2, but I want to continue using the 50,000, right? And Excel assumed I wanted to move to cell C13, which is blank, right? So it's trying to do C2 divided by C13. There's nothing in C13. So to make it keep this cell static, right, instead of jumping a cell each time it does the division, I have to use dollar signs. So I go back to my original formula. I'm going to put some dollar signs around the letter B. So if I put dollar signs, this is how you tell Excel to keep B constant and not jump C, D, E every time you move over. So we hit enter, and then I'm going to redo my click and drag thing, and I get all my standard quotas. And then I should add these up to make sure that I did everything right. Do the sum of these 6 numbers. And what should I get? 250. All right, I need the lower quota now. So I need to know what these guys are rounded down, right? I have to chop the decimal off. So Excel has a command to do that, and it's called the round down command. So we type equals round down, no space. Yep, just round down, no space, and open up parentheses, and then you have to tell it what cell do you want it to round down. I can't seem to click in the cell above here, so I'm going to give the address as B3. And then you have to tell, so you can see right here it says round down. It asks for what number do you want to round. And then it says, then you have to put in the number of digits you want. I want 0, right? I want 0 places after the decimal. So I'm going to put comma, because that's what it asks for. It says do number, comma, number of digits. So I do comma, 0, close parentheses, enter, and it rounds down to 32. Yeah, I'm not. It's just a space, yeah. Number, digits, yeah. Sometimes you have to do a little interpretation because they use shorthand for things and stuff. All right, and then you can just click, drag, rounds them all down. I should add them up. Sum, oops, of these 6, 246. So now I need the residues, right? I need the leftover part. So I need to somehow make Excel do the calculation that will give me 0.92 and 0.72 and 0.08. That'll give me the decimals. I could subtract. Yeah, I could do 32.92 minus 32. That'd give me the 0.92. So I do equals this minus, nope, not that, minus B4. And I get the 0.92 as the result. Click that, drag it across, and I have all my residues. Yeah, if I add them up, I know that they should come out to 4. It's a good question. Why didn't I need dollar signs in this column, this row, or this row? I didn't use dollar signs. You only use dollar signs if you want it to keep a cell static. So this is the amazing thing about Excel, is that it can tell, like when I did this lower quota here, I said round down cell B3, right? It can tell that when I put that formula here, I actually want it to round down cell C3.
So it's when you have two cells that you're dealing with, you have to isolate one.
If you want to isolate, if you want a cell to stay static.
We're dealing with one cell at a time, and it's intuitive.
No.
Dollar signs, it would have done 0.92 down the whole row.
Yeah, yeah. If I had used dollar signs, it would have been using that formula the whole time.
Since you're only asking to round down one cell at a time, it won't be intuitive.
Yeah. Yep. Yeah, so it intuitively knows that you want it to use the next cell in the next row. So the only reason I needed dollar signs here is because I wanted to use this cell in every formula, not moving across. Okay, so now I have to do my surplus. This is the hard piece of the command. As a human brain, it's easy to pick out. I says, okay, I need to give out 4 seats. This number's here. And I have to figure out which of these is the largest 4. Telling Excel how to do that is a kind of a complicated command. No. No, because listen, when you do this for the project, you're going to have 50 states. And you might have to give out 15 surplus seats, and you're going to have to search through 50 decimals to find the top 15 in size, right? But the whole idea is to get Excel to do that work for you, so you don't have to spend your time searching. Excel will search. All right, so the command is, I can't remember. This is a very programmy kind of thing to use an if-then statement. So we want to tell Excel to say, if this number is one of the largest 4 in this list, put a 1 here. Otherwise, put a 0 here. So we'll be able to see who gets an extra and who doesn't. So if the 0.92 is one of the largest in this list of 6, put a 1 here. Otherwise, put a 0. So that's the command in English. The Excel language command is equals, because we're calculating something, if, right? And then it tells you how to do this. It says it checks whether a condition is met and returns one value if true and another if false. So we have to give it a condition, and then the one value will be 1, right? If true, give a 1, and if false, give a 0. So we open a parentheses, and it says, okay, first thing you type in is the logical test. So my test is to check if that number, that 0.92, is the 4th largest in the list. All right, so the way we do this is we want to say B5. B5, because we're typing in B6. B5 is the one we want to check, the 0.92. If that number is bigger than or equal to the 4th largest number in the list. So we can have Excel find the 4th largest number in the list by using the command large. And then my list is B5 to F5. B5 colon is how you give a whole array to F5. And then we're going to use comma 4, because I do, and I'm gonna so I always forget about dollar signs, so I'm just kind of going through this the way that I would think about it. I would forget the dollar signs, copy and paste it, and then go, oh, I must need dollar signs because it's going to do it wrong. Comma 4, and then I close that parentheses. So far I've said if B5, that's the 0.92, B5, is bigger than or equal to the fourth largest number in this list. So that's what the large command says. It says find the fourth largest number from B5 to F5. If B5 is bigger than or equal to it, return a 1. So you do comma 1, otherwise return a 0, close the parentheses, and yes, question.
Simple here. We're doing see what the state. 50 or 60 or I need to reference that.
Yeah, so instead of a 4 here, we could have said cell H5. Yep. And I would need dollar signs because I need that to be static. Yep. Yep. So I would put dollar signs here, here. So now if I copy and paste this, I get some errors here. And let's see if we can figure out what the error is. So my first formula I know is perfect because I just wrote it. If I go to my next formula, I go, oh, look, it changed the list. Instead of going from B5 to F5, it thinks I want it to go from C5 to G5. It moved everything over 1. So I need some dollar signs around my letters. Dollar sign, dollar sign. Sorry, thank you. Okay, now I'm going to copy and paste this again. Why do I have all 1s? Oh! Oh, what happened?
You have to do it with less than.
You need a number, you don't.
H5 should work. Yeah, let's just try the 4. It's B5 to, oh, I have to go to G5. B5 to G5, yeah. There we go. There we go. I just was looking at the wrong array. Yeah. So this is a huge part of using Excel is troubleshooting, like when it doesn't do what you want it to do, is to figure out. And that's the frustrating thing about any programming thing is that it doesn't do what you want it to do. It does what you told it to do. And sometimes there's a disconnect, right? So once I add up my surpluses, I should have 4, right? If I did it right. Good. Okay, so I gave out 4 extra seats. And then to get the final apportionment, I'm just going to add the lower quota plus the surplus, right? Because some have 1 and some have a 0. So this is going to equal lower quota plus the surplus, which is in B6. And I should not need dollar signs for this guy. When I do my final check here, if I add these all up, I should have, what? 250. Got it. So there's Hamilton's method in Excel. Refer to this video, refer to the handout if this is new to you.